So far in this chapter, we have only considered replication architectures using a single leader. Although that's a very common approach, there are interesting alternatives to it. Also, single leader based replication has one major downside. There's only one leader there, and all the writes must go through it. So if you can't connect to the leader for any reason, for example due to a network interruption between you and the leader, then you just can't write to the database. A natural extension of the leader-based replication is to allow more than one node to accept the writes. So replication will still happen the same way. Each node that processes a write, it must forward the data change to all the other nodes. We call this a multi-leader configuration, also known as a master-master or an active-active replication. So in this setup, each leader simultaneously acts as a follower to the other leader nodes. So it rarely makes sense to use a multi-leader setup within a single data center because the benefits of that rarely outweigh the added complexity. So there are some situations in which this configuration is reasonable. Imagine you have a database with replicas in several different data centers. You might want to use multiple data centers so that you can tolerate the failure of an entire data center, or perhaps even in order to be closer to the users. Now with a normal single leader based replication setup, the leader has to be in one of the data centers only, and all the writes will go through the data center. Now in a multi-leader configuration, you can have a leader in each of the data centers. So this image, it shows what this architecture might look like. So within each data center here, we have two data centers, data center 1 and 2. So within each of these, a regular leader follower replication is used. So this, both DC1 and DC2, they both have their own leaders and followers. So in between these two data centers, each of these leaders, it replicates its changes to the leader in the other data centers. So whenever this leader node, it gets any change from a user, then it will also update it to the leader in the next data center. And the same will be done by the leader of this DC2. So when we try to merge the writes of these two leader nodes, then there's a conflict resolution involved because we don't know whether we keep the writes from the leader of DC1 or DC2 or whether we want to keep them both. So we'll discuss some conflict resolution algorithms later in this chapter. Now let's compare how the single leader and multi-leader configurations fare in a multi-data center deployment. So in a single leader configuration, every write must go over the internet to the data center with a leader node. Now this can add a significant latency to the writes and might contravene the purpose of having multiple data centers in the first place. On the other hand, in a multi-leader configuration, every write can be processed in the local data center and it's replicated in an async way to the other data centers. Therefore, this inter-data center network delay is hidden from the users, which means the perceived performance may be better. Also, in a single leader configuration, if the data center with the leader node fails, then the failover process can promote a follower in other data center to be a leader. Now, in a multi-leader configuration, each data center, it can continue to operate independently and replication will catch up when the failed data center comes back online. So also the traffic between data centers usually it goes over the public internet, which may be less reliable than the local bandwidth within a single data center. A single leader configuration is very sensitive to problems in this inter data center link. A multi-leader configuration with async replication can usually tolerate the network problems better. A temporary network interruption, it won't prevent the writes from being processed. So another situation in which the multi-leader replication is appropriate if you have an application that needs to continue to work when it's disconnected from the internet. For example, the calendar apps on your mobile phone, your laptop and other devices. In your calendar app, you can see your meetings, which is a read request, and also create new meetings, which is a write request at any time, regardless of whether your device currently has an internet connection or not. So if you make any changes when you're offline, they need to be synced with a server and your other devices when your device is next online. So in this case, every device has a local database that acts as a leader. It accepts the write request, and then there's an async multi-leader replication between the replicas of your calendar on all the devices. Now this replication lag may be hours or even days depending on when you have internet access available. So from an architecture point of view, this setup is essentially, it's the same as multi-leader configuration between data centers. So in this case, we are considering that each device is a data center and the network connection between them is extremely unreliable. Another use case is real-time collaborative editing applications. So they allow several people to edit a document simultaneously. For example, Google Docs, Etherpad, they allow multiple people to concurrently edit a text document or a spreadsheet. Now, so in Google Docs, when one user edits a document, the changes are instantly applied to the local replica, which is the state of the document in the web browser or client application. And then it's replicated in an async way to the server and any other users who are editing the same document. So for faster collaboration among multiple users, generally Google Docs, it does not have any locking at the document or the row level. So this approach, it allows multiple users to edit the same document simultaneously, but it also brings the challenges of multi-leader replication, which requires handling the conflicts also. The biggest problem with multi-leader replication is that write conflicts can occur, which means that conflict resolution is required. So for example, in this diagram, in this image, consider a wiki page that is simultaneously being edited by two users. So user 1 here, it changes the title of the page from A to B. So it sends an update request to this leader here. And user 2 here, it simultaneously updates the title of the page from A to C, and this is happening at the same time. So it sends the request to leader 1 and user B is sending the request to leader 2. Now each user's change is successfully applied to the local leader. So for user 1, this is the local leader L1, and for this user L2 is the local leader. So however, when these changes are asynchronously replicated, now then a conflict will be detected. So this problem won't occur in a single leader database. So when this L1 and L2, they try to merge their changes together, then there's a conflict. So the simplest strategy for dealing with conflicts is to avoid them. I know it sounds strange, but this is the best strategy of dealing with conflicts. So if the application can ensure that all the writes for a particular record, it goes through the same leader, then the conflicts won't occur. So the conflicts only happen if for the same record, two different writes are made to two different leaders, as we saw in the last image. So then the system has to figure out which write it has to keep, which has to discard or merge. Now, since many implementations of multi-leader replication, they handle conflicts quite poorly, avoiding this conflict is a very common thing, common and recommended approach. For example, in an application where a user can edit their own data, like their profile picture, you can ensure that requests from a particular user, they're always routed to the same data center. So different users may have a different concept of a home data center, which can be picked based on the geographic proximity of the user. But from any user's point of view, the configuration is essentially just a single leader. However, sometimes you might want to change the designated leader for a record, perhaps because one data center has failed and you need to reroute all the traffic to a different data center. Another case can be when a user has moved to a different location and is now closer to a different data center. So in this situation, conflict avoidance will break down and you have to deal with the possibility of concurrent writes on different leaders. Now, every replication scheme must ensure that the data is eventually the same in all the replicas. So thus the database must resolve the conflict in a convergent way, which means that all the replicas must arrive at the same final value when all the changes have been replicated. So there are various ways of achieving this convergent conflict resolution. The first one is last write wins approach. As the name suggests, you give each write a unique ID, which can be a timestamp or a UUID. and then pick the write with the highest ID as the winner and throw away all the other writes. So this approach is quite popular, but it's dangerously prone to the data loss also. Because if you are picking just one write based on timestamp or UID among different writes, then there can be data loss. So we'll discuss last write wins in more detail at the end of this chapter. Another approach is that you give each replica a unique ID and let writes that originated at a higher numbered replica always take precedence over the writes that originated at a lower numbered replica. But again, this will also imply some data loss. Another approach is that you can record the conflict in an explicit data structure that preserves all the information, and write application code that resolves the conflict at some time later, maybe by prompting the user with both of these versions, and the user can pick which one to choose, or whether to pick some part from the one and some part from the other. So we can show these multiple versions to the user and ask them to pick some version of those changes. Now let's talk about replication topologies. So a replication topology describes the communication paths along which the writes are propagated from one node to the another. In case you have just two leaders, there is only one plausible topology, and which is that the leader 1 will send all its values to leader 2 and vice versa. Now if you have more than two leaders, there are various different topologies which are possible. The most general topology is all-to-all topology, which is the third one here, in which every leader, it will send its writes to all the other leader, like every other leader. So however, there are more restricted topologies which are also used. For example, MySQL by default, it supports only a circular topology, which is this one. So in this topology, every node receives a write from one node and then forwards those writes to one another node. So another popular topology has the shape of a star, where one designated root node, it will forward the writes to all the other nodes. Now a problem with circular and star topologies is that if just one node fails, it can interrupt the flow of replication messages between the other nodes, causing them to be unable to communicate. Now the fault tolerance of a more densely connected topology such as all-to-all is better, because it allows the messages to travel along different paths, because there are many different paths in that topology, and thus it avoids a single point of failure. So on the other hand, all-to-all topologies can have issues too. For example, some network links may be faster than others due to network congestion, and it can lead to some replication messages overtaking others. So let's understand this with an example. In this image, we have a client A here, which inserts a row into a table on leader 1. This is the insert. And client B, which is here, it updates that row on leader 3, which is L3 here. However, leader 2 may receive the writes in a different order. So this is the leader 2. It may first receive the update, which from its point of view is an update to a row which does not exist in the database, and only later receive the corresponding insert, which should have preceded the update. So this is a problem of causality, as we discussed in the last video, similar to the one we saw in the case of consistent prefix reads. So here the update depends on the prior insert. So we need to make sure that all the nodes process the insert first, and only then they process the update. So simply attaching a timestamp to every write here is not sufficient, because clocks cannot be trusted to be sufficiently in sync to correctly order these events at leader 2. Now this clock sync problem we'll discuss later in chapter 8. So to order these events correctly, a technique called version vectors is used, which we'll discuss later in this chapter.